Okay, for section 2.7 we are looking at polynomial inequalities and rational inequalities and solving and graphing on a number line. And so we'll do two problems today to help you out. I'm going to take a look at it's number 24 from your book. You don't have this problem in your homework, but if you wanted to look at it, it's 24 from your book. It solved the inequality and then graph the solution or solutions on a number line. And so this is just a normal polynomial. And then the other one I'm going to do is number 49 from your book, which again I don't believe you have that on your homework, but it solved the inequality, and this time it's a rational function, and then graph the solutions on a number line. So they're similar, a little bit more work to do with this one, but similar idea. Alright, well, I'm basically going to figure out what the x-intercepts are, or I kind of going to graph this like we did in the previous section. First thing I want to do is make sure that this is equal to 0 before I do anything with it. So I'm going to say that 2x to the third plus 13x squared minus 8x, and subtract 6 from both sides so that this is minus 52 is greater than or equal to 0. And then I'm going to go ahead and try to I guess do synthetic division since this is to the third power. So if you again want to kind of speed the process up, you can easily take out your calculator and graph this so that you can see what the x-intercepts are. Said overall that's fine as long as you show me the work afterwards. So 2x to the third plus 13x squared minus 8x minus 52. And I'm going to go ahead and hit graph, and basically the graph that you're looking at is kind of what we're going to be doing here. Alright, so it looks like I can see there's one at 2, so I'll go ahead and do the synthetic division with 2. So 2, 13, negative 8, negative 52, and I'll plug in 2, drop down the 2 and multiply, and then run through your process of multiplying and adding and multiplying and adding. Multiply to get 34, add to get, looks like 26, multiply to get 52, and sure enough, that will give me a 0. So I know this factors into x minus 2, and now I can take a look at this, 2x squared plus 17x plus 26, and I can try to factor that further. And if that's throwing me trying to factor it, you can always use the quadratic formula. Again, it's whatever kind of comes to you when you're doing it. So I know this is going to factor into x minus 2. And now look at this. Now I can obviously take a look at this and say, well, maybe I can just figure out on my calculator what it is. Looks like it's in between. I can't tell if it's... It almost looks like it goes through negative 2, but I'm not sure. So again, if you want to try plugging negative 2 in through synthetic division. So 2, 17, 26. As long as you know that deep down the idea is you would either be factoring or using the quadratic formula to find this. It's fine if you use your calculator to kind of assist you through it. Just make sure that you understand again how it works, because if you don't, when it comes time for the test and you have to actually do this because you won't have a calculator to help you out, you're going to be a little bit lost. Alright, so it looks like it does work. So x plus 2 is another factor, and now this is linear. This is actually 2x plus 13. If I set that equal to 0, I get negative 13 halves, or that actually is the factor I want. It's 2x plus 13. And I'm saying that that is greater than or equal to 0. So these two are the same thing. This one's factored. And what I'm going to do is I'm going to draw a graph like we would have done in one of the previous sections. We're using the end behavior and that sort of thing. I'm going to do basically this graph on just a number line. If you want to imagine a little y-axis here, you can. I know this is going to be 0. I'm not going to sit and draw all the tick marks out, but if I wanted to, I could easily do so. I need to go and cover negative 19 or negative 13 halves, and so normally when I do this, I don't require you to write out all these tick marks. We know what a number line looks like. I'm just going to say, okay, here is 2, here is negative 2, and then here is negative 13 halves. And you don't even have to put any of the tick marks on there. Alright, I've got the x-intercepts. I'm going to go ahead and look back at the inequality. Notice that it's equal to, which means I should include this on my number line, all of these points. And now think in terms of what the graph would look like. If I used the end behavior rules, if I look at the leading term, the leading coefficient is positive, which means it's going up on the right. highest exponent is odd, which means it goes the opposite direction on the left, so it's going down. None of these x-intercepts or roots or zeros are multiplicity 2 or any even number. So my graph is going to look something like this, without getting too specific in terms of how high or low it's going. And now look back at the problem. It says, where is this function, whether you look at this one or this one, where is this function greater than or equal to 0? Well, that's wherever it's above the x-axis or your number line. So that's clearly here and here. So in terms of graphing the solution on a number line, all you'd have to do is draw this number line out below it again and say, well, from 2 and then everything to the right of it, because this function will continue to go to the right, so I want all of this, and I also want this, and that's between negative 13 halves and negative 2. Again, I don't need to see a lot of tick marks on here. We know what a number line looks like. Just make sure you get the numbers in the right spot. And this is what one solution would be. There's the number line part of it. In terms of solving the inequality, they're going to want you to write it out in like x is greater than or equal to 5 or something like that. So like for this particular one, you're going to say x is greater than or equal to 2. For this, because it's in between, remember to write both numbers down, put x in between them, and then the arrows will always point to the left. And so this is the solving part. So here's the solving, there's the inequality, and you can kind of see that just looking at this graph. If it was less than or equal to 0, then of course you would be looking at this, and then obviously you'd have different inequalities. Alright, so that's solving a polynomial function. Another thing you can do, once you get the x-intercepts, you could just do a test point. You could plug in a number and see, is it above 0 or below 0? Has to be 0 because the first step you're supposed to do is set it equal to 0 before you solve it. So it's another option if you like that, if you don't like doing the graphing thing. Alright, the second one, when you're graphing a rational function, we find what we call the boundary values. You might remember us talking about this in the notes. And the boundary values are two things. It's where this function actually equals 1, regardless of whether there's an equal to or not, and it's where the function's undefined. I would do the undefined things right away. You can look at the denominators and see them. I can see it's undefined at 1 and negative 1. So I'm going to say x cannot equal 1 or negative 1. Those are two numbers that have to go on my number line, and because it cannot equal it, they'll both be open circles. The other thing is, where is this function actually equal to whatever number they have over here? Where is it actually equal 1? So now I'm going to solve that for x. Alright, so I'm going to get a common denominator, and it looks like I'm going to multiply everything by the least common denominator, which is x minus 1 and x plus 1. And so if I multiply this term by both of these would cancel, and I have 5 times x plus 1 left in the numerator. If I look at the second term, the x plus 1s would cancel, and I have negative 2x times x minus 1 equals, and if I multiply both of these by 1, nothing's going to cancel. It would just give me x minus 1 times x plus 1. And if I multiply by the least common denominator, the denominator should be gone. Now I'm just going to multiply everything out and try to simplify as much as I can. Because I see that I have an x squared term in this, that means I am probably going to have to factor or use the quadratic formula. So, because I want to factor or use the quadratic formula, I want to move all the terms to one side, set it equal to 0. I like the squared term to be positive, so I'm going to move everything to the right. So I'm going to add 2x squared so that I have 3x squared over here. I have a total of 7x, so I'm going to subtract 7x. And then if I subtract this 5, it will give me minus 6. And so now it's my job to try to solve that. Try to factor or use quadratic formula. If I multiply the front and back numbers together, I get negative 18. Factors of negative 18 that I'm looking for looks like negative 9 and positive 2 will give me that negative 7. So I can rewrite this as 3x squared minus 9x plus 2x minus 6. where that is the same thing as negative 7x. And then we do our little factor by grouping trick. Factor out the 3x that they have in common, and that leaves me with x minus 3. Factor out the 2 that this set of parentheses has in common, that leaves me with x minus 3. And then they both have x minus 3 in common, so my final factored answer of this would be x minus 3 times the two things that got factored out, 3x plus 2. And it seems like a long process, and it is. Now I can set them both equal to 0 to get x is equal to 3 and x is equal to negative 2/3. And these numbers are also going to go on my number line. Alright, now before I actually write them down here for my boundary values, I got these two numbers, which is wonderful, but I need to look back at the original problem and at the inequality. It was x is less than. If I actually plugged in x equals 3 for x here, I'm going to get 1 on this side. Well, 1 is not less than 1. It's less than or equal to, but it's not less than. The point is, if this doesn't have an equal to on it, then you actually don't include either one of these numbers either. They're going to be open circles. If this was an equal to, then you would have closed circles for both of those numbers. So my boundary values, all of them together, is going to be 1, negative 1, 3, and negative 2/3. And now I'm going to do the same thing I did for the last problem. I'm not going to try to graph this because this deals with asymptotes and so on. I'm just going to draw my number line and I'm going to put the numbers in order. So I have an open circle at negative 1. I have an open circle at negative 2/3. Notice I'm not putting tick marks. I'm just writing down the numbers in the order that I would see them on the number line. Spacing wise, I don't really care. Like I said, we know what a number line looks like. And then what you're going to do is you're going to basically plug in a test point. So you're going to pick a number that fits in this region, plug it into the original function to see, is it going to give you a number less than 1 or not? Plug in a number here, does it give you a number less than 1 or not? And so on. So I'm going to write the original function down right here so that we can actually see it again. Alright, there's the original function. And now I'm going to test whatever number I want out here. So starting out here, I'm going to try negative 2 again. Please show your work for this. Plugging in negative 2, that is going to give me 5 over negative 3. Plugging in negative 2 is going to give me 4. Again, this is a negative number, so I'm changing this to plus, over negative 1. And ask myself, is that less than 1? Negative number plus another negative number, definitely going to be less than 1. So I'm going to shade this region. And typically it goes every other one when you're shading regions, but you can't guarantee that, so you do want to check. So, got to check a number in between negative 2/3 and negative 1. Yeah, that's a little unfortunate. So, if you want, you can get a common denominator. This is negative 3/3, negative 2/3. There's no number really in between there, so maybe change this to negative 6/6 and negative 4/6. So I'm going to plug in negative 5/6. Again, probably won't have to do this very often, hopefully, anyway. So it looks like I'm going to have 5. Negative 5/6 minus 1, or negative 6/6, is going to give me negative 11/6. We'll worry about simplifying it later. That's going to become plus, because it's a negative number. That's going to end up giving me 10/6, or 5/3, divided by negative 5/6 plus 6/6, or 1/6. Okay, now I'm going to have to do some simplifying work here. Multiply by the reciprocal, that's going to give me negative 30 over 11. This one, if I multiply by the reciprocal, it's going to give me 30 over 3, or of course 10. And you're asking yourself, is that less than 1? That's pretty close to negative 3 plus 10. It's definitely not less than 1. It's bigger than 1, so I'm not going to shade that region. Alright, now pick a number in between here. If you can ever pick 0, plug 0 in. It's an easy number to plug in. That's going to give me 5 over negative 1 minus 0 over 1. And ask yourself, is negative 5 minus 0 less than 1? Sure it is. So that means I'm going to shade this region. Means I probably will not shade this, but you do have to check it because, like I said, that doesn't always work. So plug in 2. That's going to give me 5 over 1, or 5, minus 4 over 3. and you ask yourself, is that less than 1? That's just barely over -1. So it's 5 basically minus 1. That's definitely not less than, so do not shade that. The last region I have left is over here, and I'm going to pick 4 for that. And if I plug that in here, it's going to give me 5 over 4 minus 1, or 3. So 5/3. Minus, plug in 4, that's going to give me 8 over 5. And is that less than 1? Might need to get a common denominator here so that I can figure out what's actually going on. Getting a common denominator, I have to multiply by 5 over 5. So that's 25 over 15. Multiply by 3 over 3, it's 24 over 15. And is that less than 1? Doesn't look like it. And so, it looks like I'm going to end up with a graph that looks something like that. Alright, so 1/15. Oh wait, sorry, never mind. I was thinking negative. Okay, 1/15 is definitely less than 1. Yes, that means I will shade this. I knew something was up because typically it does go every other one. Like I said, it doesn't have to, but it typically does. So again, there's the number line that I'm looking for. Now in terms of the solving, you just have to write out the inequalities. So this part here would be x is less than -1. In between two numbers, so write down the two numbers in order, put x in the middle, and the arrows point to the left, and then x is greater than 3. And there's the solving part. Alright, a lot of work involved in that particular one. If you have questions or not quite sure how I got something, please let me know.